Okay, Assalamualaikum and good morning. Can you hear my voice? Okay. Okay. So the times now is 11:01. So maybe we can start our class to proceed our discussion on SVM topic. So this is the last section of the SVM. Okay, before we start to discuss for the last section, so maybe we can have some revision. Okay, last week we have discussed on how to derive some important equation. For example, calculation of on times of the vectors TA, TB, and TZ. So in derivation, we start. You need to support your derivation if, for example, if there in final exam question or midterm test ask you to derive. So make sure your derivation you need to support with suitable diagram. For example, like this. So make sure you start put the diagram in general representation. So means your derivation valid for any sector. Sector 1, 2, 3 until 6. Okay. Okay, then you calculate using the trigonal function or identity. So make sure you draw properly or in geometrically to calculate all the component of vectors. Okay. So then actually the space vector you can write or you can write for various form. So for example, this case in alpha and beta, which is in rectangular form, or you can write in component vector for this case. This equation 15. Okay, then you apply all the equation based on the information given in the vector diagram. So then finally you can derive the calculation of TA, TB, and TZ. Okay, then we have discussed already the switching of vectors. For this case, we discuss only for sector number 1. So you can see the space vector is located in sector number 1, where the two adjacent vectors are V1 and V2. So the zero vector is V0 or V7. So actually for one sampling period, so remember your sampling period start from 0 here, 0 second. Then you need to sketch the switching pattern for one complete sampling period TS. For example, the value is 100 microsecond. So one complete sampling period you can divide into 8 intervals. So you have to take note that the selection of vector at the beginning of the sampling period, the modulator must choose 0 vector. So where the state is 0, 0, 0. And at the end of sampling period means interval number 8. So you can see interval number 1 and interval 8, you have to choose 0 vector, V0, where the states are 0, 0, 0. But at the middle of the sampling period, where in interval 4 and 5, so this interval you also choose the 0 vector, which is V7, but the state combination are 1, 1, 1. Okay. So then other interval, you have to choose the adjacent vectors, V1 and V2. So since the adjacent vector for the space vector, when the vector is located in sector 1 is V1 and V2. So then here for the case when the space vector is located in middle or in between V1 and V2. So means the angle difference between the space vector here and the V1 for this case is theta 1 is 30 degrees. And the angle difference between the space vector and V2, so means this angle. So here is theta 2, which is also 30 degrees. Since the angle size, the sectors are equally divided into 6 sectors. So mean each sector have the same size, where the angle difference between V1 and V2 is 60 degrees. So this case, your V is at the middle. So means you can notice from the switching pattern here. where your TA or T1, the interval size is same with the T2. TA and TB are same. Okay, because the vector is located at the middle between V1 and V2. So then we have discussed the effect when you try to change the location of the space vector. So this case, your space vector now is close to V1 by drawing the component vectors involved to get the resultant vector V. So then you have VA TA per T, you summing with the VB TB per T, and of course the zero vector. So this component of vector, the vector that I highlighted with the yellow color here. So we can notice by drawing the component vector where the length of the component vector VA TA T, or maybe we can define this vector as UA. Here will be UB. So where the length of the vector UA is larger than the amplitude vector of UB. So that's why this case your TA, the time taken for applying voltage vector VA or V1 is longer compared to the time taken to select vector V2. So mean TA is larger than TB. Or means specifically T1 is larger than T2. So same goes to the other side. So this because we apply the symmetrical approach. So here is the symmetrical axis here. So where you can see here TB, same with the TB we define on the left hand side here, which is smaller than TA. Okay. Okay, sorry, this one you must divide by 2 because in one sampling period, the vector, the adjacent vector is switched twice, 2 times. So that's why you need to divide by 2. But for the zero vector, because it involve 4 intervals, so your TZ must divided for each interval you must divided TZ with divide by 4. Okay. So this case when your space vector is close to V1, and here when the space vector is close to V2. Okay, so you can notice here, since your UB now is larger, the amplitude of UB is larger than UA, so that's why the ratio TB and T is larger compared to the TA per T. So means here by looking at the switching state waveform here, so then you can notice here this interval is larger than compared to here. So mean the interval here is TB divided by 2, here will be TA divided by 2. Alright. Okay, this one, the effect when we try to reduce the amplitude of the space vector. So you can see this vector now is shortened. So this case, the effect on TZ will be longer because the amplitude of the new vector now is smaller compared to the previous one. Okay, so this is the effect when we try to change the location of the space vector. Okay, now for today, we discuss for the last section the sequence of the switching vectors. Okay, so we start from sector number 1 here. Sector number 1. Okay, so mean your vector now is located for the first 60 degrees. So here is 60 degrees. So remember for each side of the sector is 60 degrees. So for the case of the vector is located in sector number 1. So as discussed in previous pages, at the beginning of the sampling period, so this is the sampling period. So mean at the beginning here, interval number 1, and at the end of the interval number 8. So this case, the modulator must choose the zero vector. So where the combination of state is 0, 0, 0. So same goes to here, 0, 0, 0. And at the middle of the sampling period, which is interval number 4, here is 4 and 5. So these two interval, the modulator must choose 0 vector, but the combination of switching state now is 1, 1, 1. Okay, so here is 1, 1, 1. Okay. Okay, then for the selection of adjacent voltage vector, which are V1 and V2. So at the beginning, start from V0, right? V0. Then the vector or the mapping vector will be jumped to vector V1. So this is for the interval number 1. Then for the second interval, the modulator must choose V1 vector. So here will be V1 vector. So where the combination of switching state is 1, 0, 0. So this will be 1, right? Here maintain 0 and 0. Okay. So mean your switching state is suddenly changed from 0 to 1 when it enters to the interval number 2. Okay. So since we apply the symmetrical approach for SVM, so mean interval number 2 and interval number 7 has produce same switching state. So mean here will be 1 and 0, 0. 1, 0, 0. So means the modulator choose voltage vector V1, 1, 0, 0 here. Okay. So mean when it transit from interval 7 to 8, the switching stated SA is suddenly change the state from 1 to 0. Okay, clear? And interval number 3. So means the vector of the mapping of the vector now is jumped to this point or vector V2. Vector V2. So mean the state for the vector V2 is 1, 1, 0. So mean for interval number 3 here is number 3. Sorry. Interval number 3. So mean the state for interval number 3 is 1, 1, 0. Here will be 1. Then for SB suddenly change from 0 to 1 and 0. SC is 0. Okay. Then this combination state same to the interval number 6, right? Interval number 6. So where 1, 1, 0, here will be 1. Then here also 1. And here suddenly change to 0. Okay, then you can complete the sketch of the switching state waveform. Okay, so this is the switching pattern for this case when your space vector is located in sector 1. So then you can you can analyze the way the vector are chosen starting from 0, then it will be switched to V1, then it will go to starting from 0 go to V2 V1, then it will choose V2, then at interval number 4 the vector located at origin indicates that the modulator choose V7 1, 1, 1. Then it will return from V7 goes to V2. Okay. Then V2 switch to V1. Then finally from interval 7 to interval 8, it will end the selection of vector at the origin. So mean the vector V0, 0 vector. So this is the sequence of the switching vector for the case when your space vector located in sector number 1. Okay, clear? Ada 2 student here. Thank you for coming. Syafiq and Fahmi. Tak balik raya Okay, class. Okay, so far. Any question? Boleh dengar 11 suku. Okay, now we try to analyze the sequence of the switching vector So this case, when your space vector now is located in sector number 2 here, sector number 2. Okay. So this is your space vector now. Where the angle is, for example, this case as example is 90 degrees, which is in line with the Q axis. Okay. So remember, for any sector, in a sampling period, the modulator must choose zero vector. Ni zero vector. So it's the must. Zero vector here. So here also zero vector at interval number 8 at the end of the sampling period and at the middle. So this case it will choose V7, right? Where the combination of switching state is 111. Okay, clear? So here is V0. Then here for these two interval 4 and 5, sorry. So this case the modulator must choose V7. Here will be V0. Okay. Yeah. Sketch properly. Okay, now for interval, okay, this is the interval number 1, interval number 4, 5, and 8. Okay. So how about the selection of vector for interval number 2 and 3? Can anyone give the answer? Shafiq? Yeah. For interval number 2. So for this case, when your space vector is located in sector number 2, so firstly you need to identify what are the two adjacent vectors. So the two adjacent vectors are V3 and V2. So remember, you must apply this equation. So where your space vector, you can write the equation of the space vector is V3. You multiply by its ratio. Then summing with another adjacent vector is V2. Multiply with its ratio T2 divided by T. And the zero vector. So Vz can be V0 or V7. So I just put subscript Z here. So multiply with its ratio Tz divided by T. Okay, so there are two adjacent vectors are V2 and V3. Okay, so now we discuss the topic, the sequence of the vector. So mean the arrangement. Which vector need to be selected first? Is it for this case V2 or V3? Which one? V3 or V2? Someone please give the answer. At interval number 2. So this is your sampling period. So your times will go to here. So this is the time. Initially or at the beginning of the sampling period, choose the zero vector. And at interval number 2, which vector need to be selected? Is it V2 or V3?
V2.
Yes. Someone? V2 or V3? For sector number 1, clear. At interval number 2, it must choose V1. V1 first. But now for sector number 2, which vector, which adjacent vector need to be selected?
V2.
V3. Very good. Very good, Fahmi. Okay, so why we need to choose V3? Why don't we choose V2? Can someone give the reason or justification? Why the modulator of SVM need to choose V3 instead of choosing V2? So maybe we can say that your V3 is VA. Your V2 is VB vector. It means here, interval number 2, you have to choose V3. Interval number 3, you choose V2. And due to the symmetrical of the switching pattern here. So here interval number 6 must be V2. And V3, here is V2 for interval number 7. So means starting here, then it will jump to here, V3 first. Then go to V2. Then at the middle, located at origin, V0, V7. Then here, return V5, at interval 5. Then we'll go to V2, interval number 6. Here will be V3 at interval number 7. Then finally, at the end of the sampling period, interval number 8. So the question is, why we need to choose V3 instead of choosing V2? Okay, you see the state, so here for V3, for interval number 2, so the state of SA is maintained, right? 0, 0, 0, right? So here will be 0, 1, and 0, right? So mean for SB suddenly change to 1. Is it right? Here will be 0, right, for AC. 0, 1, 0. So same goes for interval number 7 here, right? Because this is symmetry waveform. 0, then here will be 1, then suddenly change to 0. Here will be 1. Okay, 0, 1, 0. Okay. So if you looking at the switching state waveform from interval number 1 to interval number 2, so you can notice that the switching only occurs at phase B. Is it right? Phase B only. So mean your top switch for the phase B or leg number 2 of the inverter, the top switch is switched from off state to on state. So mean it only involve switching at phase B. Phase B. So let's say we at interval number 2, we consider it with the modulator switch vector V2. The modulator switch vector V2. So means the switching occurs at phase A and phase B because your state for V2 is 1, 1, 0. Clear? 1, 1, 0. Initially, the state is 0, 0, 0 at interval number 1. Then when it enters to interval number 2, the state change 1, 1, 0. So mean the switching occurs in phase A and phase B. So mean the number of switching increase compared if you choose the modulator choose voltage vector V3. Because for vector V3, the switching only occurs in phase B. So we try to minimize the number of switching. And so mean we try to reduce the switching frequency and hence the switching losses. So mean we can improve the efficiency of the inverter. Clear? So that is the reason why we need to choose vector V3 first. Why? So mean here your at interval number 3, then we can completely sketch the switching pattern waveform. V2 is 1, 1, 0. Then your SA suddenly change to 0 to 1. Then same goes to here. Okay, then for V2, 1, 1, 0. So this maintain 1. Here will be 1. Then for AC, here maintain 0, right? Maintain 0. Okay. Okay, clear. Okay, then we can completely provide the timing information for each interval. So means here will be what? T0 divided by 4. Here will be T3 divided by 2 because you have two interval here. T3 divided by 2. Here T0 divided by 4. Then the zero vector, you have 4 interval. T7 and T0 are same. Sorry, take note that T0 and T7 same. Then here will be divided by 4. Here divided by 4. Then here, time taken to choose voltage vector V2. So T2 divided by 2. Here also T2 divided by 2. Okay? Clear? Faham Okay, now we move to the third case, sector number 3. So this is sector number 2. Okay, for the sector number 3. Okay? So far okay, class? Okay, senang ni. Okay, we go for sector number 3 now. So this case, your space vector is located in sector number 3. So this is your space vector. The voltage space vector. Okay. Okay, so remember at the beginning, at the middle, the modulator must choose 0 vector. So here must be 0. Here also 0, 0, 0. Here 0, right? 0. Okay. Okay, now sector number 3. So first you need to identify what are the two adjacent vector. So which are V3 and V4, right? So which adjacent vector need to be chosen? V3 or V4? You start at interval number 1, the state are 0, 0, 0. So we try to minimize the number of switching, to minimize the switching losses, and then we can improve the efficiency, the power efficiency. So of course, you have to choose V3 because the switching only occurs in phase B. Baguslah. Okay. So at interval number 2, so you have to choose V3. So mean at the starting here, at the origin, then the modulator must choose V3 at interval number 2. So here 0, 1, 0. So same goes for interval 7 kan? Interval number 7. So here must be 0. Here will be 1. Then suddenly change to 0 here. Here will be 0. So this state is 0, 1, 0, which is vector V3. Right. First interval 0 vector. Interval number 8, 0 vector. Interval number 7, V3. Okay. Okay, then it will jump to V4. And for a third interval, V4. So this is number 3, interval number 3. So in this case, you have to choose voltage vector V4. So where the state are 0, 1, 1. So here will be 0, 1. Suddenly SC suddenly change to 1, 0, 1, 1. So same goes to interval number 6. Okay, here is interval number 8. 0, 1. Here will be 1, right? Okay. Okay. So then the mapping of vector jump to at the origin, interval number 4. And also the vector will be stayed for interval number 5. Then it will return and will be written 6, 7, and finally 8. So then at the middle here, so the modulator must choose V7, V7 or 0 vector. So where the state are 1, 1, 1. Okay. Okay, so this is V7. For interval number 4 and interval number 5. So make sure you must complete your sketching, your sketch with the timing information. So here will be T0, T7, T7, T0. So make sure you must divide the time with 4 because you have 4 interval here. Okay. Okay, then here for the time taken to choose V3 is T3. Here also T3, right? Here will be V4. So you must divide by 2. Okay. Then here T4. T4. Okay, clear. Okay, then we go for sector number 4. Sector number 4 here. So where your space vector now at this point. So this is your space vector. So the two adjacent vectors are V4 and V5. Okay, so you have now you can sketch. So starting from 0, here will be 0, 0. Then which vector need to be selected first? V5, because the switching only occurs in phase AC or leg 3 of the inverter. So mean your switching status AC suddenly change from 0 to 1. Okay, so this for the first interval. Sorry, maybe I 1, 3, 4, 5, 6, 7, 8. So at the beginning 0 vector, then it will jump to number 2 kan. Here V5, then jump to V4, 4 here, stay at origin 5, then they return kan, return back to V4, 6, 7 and 8. Okay, so this is the sequence. So mean interval number 2 jump to 0, 0, 1. Sorry, here will be 0. Here also 0. Okay, this one 1. Then for interval number 3 here V4, you must choose V4. Here V3. V4 is 0, 1, 1. 0, 1, 1. Here maintain 0, right? Then SB here suddenly change to 1. Here maintain 1. Okay. So then for the at the middle of the sampling period, interval 4 and 5, you must choose V7, 1, 1, 1. Clear? Then since we apply the symmetrical approach, so mean the switching pattern waveform must be in symmetry lah. So mean 6 and 3 interval give same switching state. Here will be 0, right? Sorry. Ini salah ni. Here for SA suddenly change from 0 to 1 because you must choose 0 vector V7 where the state are 1, 1, 1. Okay, clear? Okay. Sector 3, sector 4. Okay, betul. Here maintain 0. Okay, clear? Okay, don't forget to put the timing information here. T0, T7, T7, T0 divided by 4 here. Here divided by 4. Here must be T3. Divided by 2. Here also T3. T4 divided by 2. T4 divided by 2. Okay. So for this case, when your space vector located in sector 4, your VA will be V5. Right? And your VB is V4. So mean here, your TA will be, since your VA is V5, your TA will be T3. Alamak, sorry. Here should be, macam mana boleh V5? So this is the V5, right? Subscript 5. V5, here T5, T5. So your TA is T5. And TB is T4. Okay, so you can apply the equation that we have derived for the section of derivation of time information kan. Because the derivation of the equation valid for any sector. So the important thing you need to identify which are the TA and TB. So this case TA is T5, TB is T4. Okay. Okay, sector 5 tak ada apa lah. So mean same process lah or same analysis you can apply. So this case sector 5. So the adjacent vector is V5 and V6, V5 and V6. So where your switching pattern waveform is, so you can sketch 0 here, here will be 1. Okay, for SB, 0 maintain, and at the middle of the sampling period, suddenly change to 1. And for AC, 0, 1, 0. Okay. Okay, clear? So the first adjacent vector need to be selected for this case is V5 or V6? V5, right? V5. So here is V5. Then V6, V7, V6, V5, V0. Okay. Okay, don't forget to put the timing information. So you have to indicate completely the timing information. Okay, now sector 6. Here, sector 6. The two adjacent vectors are V1 and V6. So the first vector, the adjacent vector need to be chosen is V1 because the switching only occurs in phase A or in leg 1 of the inverter. So so this case the switching pattern waveform sector 6 0 suddenly change to 1 here. For SB, 0 maintain until at the middle change to 1. SC, 0 for the first two interval, then suddenly change at one state. Okay, so here V0, V7, V0, right? So the first adjacent vector to be choose is V5. Here also V5. And here will be V6. Okay, clear? So this is interval number 1, 2, 3, 4, 5, 6, 7, 8. Okay. So for in a sampling period, the vector is choose at the origin. So it will start at origin first, then it will jump to V1, then goes to V6, and then at the middle, locate at origin to choose V7, then it will return back to V6, goes to V1, and finally to be located at origin to choose V0. So this is the sequence. Okay, clear? So the important step, you must know the adjacent vectors at which the space vector is at which sector the space vector is located. So then secondly, you need to identify which adjacent vector need to be chosen. So you must consider to minimize the switching losses. So means you have to reduce the switching frequency of the inverter. So you have to refer lah or analyze the switching state when the vector change from the 0 to the first adjacent vector. So which one give the minimum change of the switching state? Okay. Okay, class? Ada faham? Understand?
Yes.
Bolehlah,
Very
doktor.
good. Orang datang hari ni. Okay, then kita boleh. So maybe we can have a break for 10 minutes. 10 minutes, 10 minutes, okay? Before we discuss the exercise number 2. 10 minit lama sangat. Syafiq, nyanyi lagu raya. Fahmi orang mana? Terengganu. Tiket dah habis dah? Tak payah balik lah. Ha? Ada lagi? Oh, balik bawa kereta. Okay lah. Jauh Syafiq duduk ni, Tangkera ni.
Jauh.
Jauh. Nanti awak nak balik raya, awak keluar highway tau. Keluar simpang apa ni? Aikro, masuk simpang 4. Ada dah rasa suasana sikit kan. Berbuka dekat arena. Kasihlah ada rasa jam sikit kan. Okay, kelas. Dah cukup 10 minit ke? Boleh lah ni. So we proceed to discuss exercise number 2. Okay, please read the question. The space vector modulation technique can be used to control three-phase inverter for obtaining the desired AC voltage. So the first 60-degree segment, so means the vector is located in sector number 1. So because your VA, your VA is actually V1. Because the first 60 degrees. So VA is V1, where the angle of V1 is 0 degrees. So mean your V1 is in line with D axis, and VB is V2. So the angle difference between V2 and V1 is 60 degrees, right? So this angle difference is 60 degrees. Okay, so you need to derive the following equation for the basis vectors UA and UB. Okay. So UA and UB equation as given in this equation below. So you need to apply this, what we call it, formula or trigonal identity. I don't know this one. So remember, you have learned this one from apa? Mathematics engineering, engineering mathematical. Ni, this one. Under topic trigonometry. Okay. So you have to apply this trigonal identity to derive the above equation. Okay, so you have 3 parts. First, you have to derive. Part B, you are given a DC voltage of 100 volt and a carrier with frequency 1 kilohertz. So where your space vector, the amplitude value is 30 volt and the angle is 25 degrees. So you have to calculate the time information using the above equation, the derived equation here. Maybe this one, equation number 1 or equation number 2 and equation number 2. Okay, you calculate the timing information in part B, and part C you have to sketch. Actually, this is the switching state waveform. It's not the inverter phase voltage. Switching state waveforms, which are SA, SB, and SC. Okay. Based on the sketch is based on the timing information calculated in part B, just only for one complete cycle of the carrier waveform. Okay. So include the timing information on the vector diagram. Okay, so first in part A, to derive these two equations. Okay, to answer this question. Okay, so you need to redraw this space vector. Please redraw this space vector. So maybe for me, I just copy here. So this is the part 1. We saw for part 1 now, the derivation. So here, okay, good. Okay, you draw this figure 1, vector diagram in figure 1. So please draw properly. A and B, maybe you can use projector. Protector. So make sure your VA and VB, the angle difference is 60 degrees. So please draw in geometrically lah. Maybe you can apply geometry tools, protractor, projector, and so on. Projector pula. Projector. Protector. Okay. So to answer this, to derive the equations, so maybe you can, so this is your space vector. So this is your space vector, right? So where your space vector, it consists of the magnitude. So you must write in capital letter and the angle. So where the angle is alpha, right? And because the angle difference between space vector and VA. So your VA is your D axis, is alpha. Okay. Okay, then you can sketch the component vector involved to produce the resultant vector V. So this is your V beta, or maybe you can, sorry. So maybe we extend this line. So actually this is your V beta, the imaginary axis voltage. So here is the origin. Then you can draw also the V alpha vector. So here is V alpha. Okay, V alpha. So where your space vector, you also can write into rectangular form, which is V alpha plus J V beta, right? Okay. Okay, then from here, in derive the equation, so you have to draw some component vector, some important component vector. So where the component vector is defined from this point to here. Okay. So this component vector, we define it as what? This one, maybe we put what? Okay, you can obtain this component of vector by applying trigonal function. So let's say to calculate V beta, to obtain the V beta, here V beta. So you can use this equation, right? Where your sin alpha is the ratio between the opposite of the triangular. Opposite is V beta. Then you divide by what? V. The amplitude of space vector V. Where the V is the hypotenuse of the triangular. Is it right? Is it true?
Yes.
Okay, then applying the trigonal function, you can also obtain for you can get this relation actually, where sin 60 degrees. 60 degrees where? This point. Yeah, here will be 60 degrees. So same goes the different angle between this vector VA and VB. VA and VB. Okay, here will also 60 degrees. So you can notice here the projection line here must be in parallel with vector VB. So that's why you get same angle here, 60 degrees. Here also 60 degrees. Okay, clear? So mean your sin 60 is the adjacent. The adjacent is what? Adjacent of the triangular. So you maybe you can concentrate for this triangular. Okay. So where the edges, the opposite of triangular is V beta. V beta. Then divide by, is it right? Sine V beta. Ayolah. V beta and UB. Okay, clear? UB So kalau you refer from the question, actually we have defined here. Ni. This is UA and UB. So mean the length from origin to here is UB. And this component vector, the length from origin, the amplitude is UA. Okay, clear? So mean here is UA. This component vector is UB. So mean by applying the trigonal function, then you get sin 60 degrees is the ratio between V beta and UB. Clear? So mean this length, this component vector. Here is UB. Okay? You get it? Boleh? Okay, then we equate these two equation to solve V beta. So where you get V, you multiply by sine alpha for the first equation. Then V beta also can be written as UB sine 60 degrees. Using equation number 2 here. This is equation number 1, 2. Okay, clear? You just equate both the above equation to solve V beta. V beta. Okay, then using equation ni, you can proceed to solve UB. UB is the ratio between V sine alpha, then you divide by sine 60 degrees. Okay, clear? From the above equation, you rearrange to solve UB. Okay, we know that sine 60 degrees, you can also write as sec3 divided by 2. Please check using calculator. And sine 60 degrees, then you can get same answer by dividing between sec3 and 2. Right? We dapat maybe 0.866 ni tu. Cuba try. Sine 60. 0.866. Same answer with when you divide between sec3 divided by 2. Betul tak? Sec3 divided by 2. Okay. Okay, then you can rearrange, you substitute the sine 60 as sec3 divided by 2. Then finally you get UB as V multiplied by sine alpha. So this will be we define as equation number 1. Sorry. Ini equation number 1. Okay, clear? So mean you have derived equation for UB. So refer to the question in part 1. So then you have derived equation number 2 now. Betul 2 divided by sec3 V and this equation. Okay. V sin alpha. Betul kan? 2, 3. Okay. Right. So now we proceed how to derive equation number 1. UA, for UA. For UA, okay, we know that, sorry. Based on the space vector diagram in figure 1, so we can calculate UA. So this is your UA. So actually UA, so UA is, maybe I use different color here, the blue color. So this component vector. So this is your UA, right? The component vector that I highlight with the blue color is UA. So mean you need to calculate the difference between V alpha and this vector. This vector. So this vector ni, I put the highlighter. This vector, yellow color. Okay. So where this component of vector, you can write the equation using the trigonometry function. So mean from here you can calculate what sine 60 and sine 60 degrees is the ratio between, sorry, this one you apply what? Cos, sorry, cos. It's not sine, cos. Cos 60 degrees is ratio between the adjacent. Adjacent is this vector kan? So maybe I define this vector as what? UX, UX. Where UX is the adjacent, then you divide by hypotenuse of the triangular, which is V, right? So then from here, you can rearrange the equation here to obtain the equation of Ux. So where your Ux is V multiplied by cos 60 degrees. Okay, clear? So to calculate or write equation of UA, so actually is the difference between V alpha and Ux, right? Betul eh? V alpha and Ux. So where your V alpha based on the V alpha actually you get from where? Okay, V alpha actually you can calculate using the trigonal function where V alpha is you multiply between V and cos alpha. Is it right? V alpha. Okay. So you refer from this triangular. Here you have here is V. Okay. Where the magnitude is V, angle is alpha. So the angle here is alpha. So this angle is alpha, right? So you can redraw lah. So the hypotenuse is V. Here will be your V alpha, right? Here is V alpha. So from here you can write the equation of V alpha. Clear? Ni same. Okay. So then you subtract with Ux. So where your Ux is V cos 60 degrees. Clear? So then you okay. So from here V cos alpha. So maybe I just rewrite this one. And pening eh? V cos alpha. Sorry, this is not V cos alpha. Cos here is UB. UB. Aduh, UB. Sorry UB. Betul kan? Tak prepare lah bicara ni. So this actually your Ux is your multiplication between UB and cos 60 degrees. Sorry So mean here Ux divide by here is UB. Sorry Clear Ada orang bertegur Okay then jap. Yang ni pun tak betul kan? Here must be UB, right? UB. Okay. So then UB, you can apply equation 1 to substitute UB. Okay. So you apply equation number 1 to substitute UB. So here will be 2 divided by sec 3 V sin alpha. Then you multiply by cos 60 degrees. Okay. Clear. Then you have to factorize the above equation. So mean you put the term of 2 sec 3 multiplied by V open bracket. Here's sec 3 divided by 2 cos alpha minus sin alpha cos 60 degrees. Close bracket. You try to factorize the above equation. So from here, actually, macam mana ni? Okay. Sin cos, okay. Ataupun I just rewrite the equation above. Sorry. V, okay, we know that sec 3 divided by 2 actually is sin 60 degrees, right? We have proof above, as above. Okay, yang ni. Okay. So you can rewrite the term of sec 3 divided by 2 as sine 60 degrees. So mean here will be sine 60 degrees cos alpha sine alpha cos 60 degrees. Okay. Okay, clear? So then you can apply the trigonal identity kan. Maybe I write using green color. Okay, green color kan. So this identity, you apply this identity sine as given in the question. So here will be what? Sine A multiplied by cos B minus cos A sine B. Okay. So then you apply the theorem for identity. So then we can reduce the equation as 2 divided by sec 3 V multiplied by sine 60 degrees minus alpha. So this is equation number 2. Okay. So now we have derived for UA and UB for part A. For part A, you have UB equation and UA equation. Okay, clear? So you can compare based on these two equations, the above and the below equation. Actually, A is apa? 60 degree kan? And B is alpha. Okay. Alright. Clear? Any question? Senang je ni. So you have two equations. Now you have solved for part A. Part A. Part B. This technique use inverter input 100 volt, carrier 1 kilohertz, and the space vector at the particular instant is located at ni, where the amplitude is 30 volt and the angle is 25 degrees. So mean this case your alpha based on figure 1, your alpha is 30 degrees, or you can write your space vector as the amplitude is 30 volt and angle is 25 degrees. Sorry, 35 degrees. Apa saya salah ni nak raya ni kot. Mood nak raya ni. Okay? Okay, you have to calculate the timing information using the above or the derived equation in part A. So, macam mana nak calculate ni? Okay, so part B. Dah laju sikit lah. Calculation of on duration. TA, TB, and TZ. So we know that your UA vector is VA multiplied to its ratio, TA per T. So this is equation number 3. And UB, component of vector, is VB multiplied by its ratio. Okay. So actually from the figure 3, figure 1. So you have here is VA. And the angle difference here must be 60 degrees. Here will be VB. So where we define UA and UB here. So this is your UA. And this component vector is UB. And by summing these two vectors plus the zero vectors, so then you can sketch for the resultant vector here, the space vector, where the vector is V. The magnitude is 30 volt, angle is 25 degrees. So this is your alpha for 25 degrees. Okay. Okay, so we have proof last week kan. Maybe you can refer to the related pages from my notes. So actually the amplitude of the active vectors or for the two adjacent vectors VA and VB, so where the amplitude are same. So where your amplitude here VA is 2/3 VDC, right? So same goes for VB, 2/3 VDC. So means we can state that your VA, the amplitude of VA and VB are same, which is 2/3 VDC. So this is equation number, this is equation number 3, 4, and 5. Okay, then to solve the problem, to derive the equation of TA, TB, and TZ, so you need to substituting. Okay, TU, equations 1, 2, and 5 into equation 3 and 4. The following equation are obtained. Okay. So equation 1 and 2 here. Equation 1 and 2 we have derived for part A. Equation 1 UB, equation 2 for UA. Then you have to substitute equation 1, 2, and 5 into equation 3 and 4 here. Then finally you can obtain this following equation. So where TA is, you rearrange equation 3 and 4. 3 and 4. TA is UA multiplied by T divide by VA, right? You rearrange equation number 3 to solve for TA. So where UA is, you substitute using equation number 2, right? Equation number 2. Where UA is 2/3 V sine the difference between 60 degrees and alpha multiplied by T. Then you divide by VA, where VA is 2/3 VDC. Okay. Or you can simplify the equation above so that you get equation number 6, set 3V VDC sine. Okay, so this is equation number 6. Okay. Okay, then for TB, you need to rearrange equation number 4. Equation number 4, TB. By TB, you ada UBT kan. You rearrange, then you get TB as UB T divided by VB. So where you UB, you substitute UB. UB you obtain in part 1. You derive in equation number 1. Equation number 1, UB. So where UB is 2/3 V sine alpha multiplied by T divide by VB. So we agree that VA and VB same amplitude. So where the value is 2/3 VDC. Okay. Then you simplify or reduce the equation above so that you get this equation. Sine alpha multiplied by T. So this is equation number 7. Yeah. Then for 0, time taken for selecting 0 vector TZ. Itulah TZ. So TZ is the difference between the sampling period and the summation of TA plus TB, right? So this is equation number 8. So we know that your T, T is the summation of TA plus TB plus TZ. So you can calculate you can calculate 0 time by rearranging the equation. Okay, clear? So actually part 2 you need to derive the equation. Or you have to calculate. You get the equation, you derive the equation first. TA and equation 6, 7 and 8. So then you can substitute all based on the information given. Then finally you can calculate lah. TA, TB and TZ. So here so apply, maybe we can write statement here, apply 6, 7 and 8 to calculate TA, TB and TZ. So where your TA is, so maybe I can write dia punya formula ni, set 3 V VDC. I just rewrite the equation, sin 60 degrees minus alpha multiplied by T. So this is equation number 6. So actually you can substitute. You can substitute all the parameters given. So here set 3, you multiply V is what? V is the amplitude, 30 volt. VDC is 100 volt. Sin 60 degrees minus 25. Okay, so don't forget your T. T is the sampling period based on the information given in the question, where the carrier frequency actually will determine the sampling period. So this carrier frequency, what we call carrier. So actually is the inversion of the sampling period T. So mean you need to divide. You have to calculate the T as this page, right? So your T is 1 divided by 1000. Okay. So remember, your T is 1 divided by carrier frequency. The carrier frequency given is 1 kilohertz. So then you can calculate. So the value of TA is 298.04 microsecond. TB is, okay, you apply this equation first, set 3. Maybe you can write the equation first, set 3 divided by VDC multiplied by sine alpha and multiplied by T. So this is equation number 7 actually. So then you substitute. So you get set 3 here. You multiply by V. V is what? 30 volt. VDC is 100 volt. Sine 25 degrees. Where your T is inversion of the carrier frequency. Then you get 219.6 microsecond. Okay, how about TZ? TZ is the difference between T and summation of TA plus TB. So this is actually equation 8. So where T is 1 divided by 1000 minus, and then you here 298.04. I just rewrite. So make sure the unit, you must put the unit here. Microsecond, or no need, I got micro, just one micro, plus 219.6 micro. Then finally you can solve for TZ as 48236 microsecond. Okay. Okay, for part B solve. Okay, part C. Part C you need to sketch the switching state waveform. Maybe yeah. Okay, you need to draw the switching state waveform. Sorry. Maybe let me copy first. Mana tadi? Yeah, okay, good. This figure. Yes, to copy. This one okay. Okay. Which page? Ni, this page for part C. I paste here. Okay, you need to completely draw the projection line and provide the values for switching state 1010, and also you need to indicate the timing information to completely sketch the switching state waveform. Okay, so means since your space vector is located in sector 1, so you have a VA, which is V1, and VB, which is V2. So this is your zero vector, V0 or V7. So mean your state, the modulator must choose the zero vector first, right? Yeah. Then your SA will be like this lah. 0, 1, suddenly change to 0. And SB, okay, this one we have discussed in section switching of vectors. For the case of sector number 1, so this is the switching state waveform. Clear? So starting from V0, then it will jump to V1, V2, V7 at the middle, V2 back, and V1, and finally V0. Okay. So you need to indicate the time information here. T0, this is T7, T7, T0. So don't forget to divide by 4 because you have 4 times to choose zero vector. Here will be T1 divided by 2. Here also T1 divided by 2, 2 times for selecting V1 and 2 times for selecting V2. Okay. Clear? So no need to put the exact numbers lah for T0, T1 kan. Because you have answer already in part B. Just put the variable lah, T1, T7, T0. No need to put exact numbers. Alright. Okay, so this is to answer for part C, part C. To sketch the waveform, the switching state waveform. So actually you need to draw properly lah. Maybe your space vector locate at this point kan. So where the angle difference is alpha, which is 25 degrees. Okay. And the amplitude is 30 volt. The angle is 25 degrees. Okay, clear? Now is what's time now?
Yes.
Bagus. Okay, before we end our lecture for today's class, so I want to demonstrate. We try to verify all the calculation that we have discussed just now. Then we verify through simulation. This is very important. Our discussion today is very important for your assignment. So make sure you understand and please watch this video, the recorded video here. Apa tadi nak buat Oh, demonstrate. We demonstrate the simulation. Start from where? I think we start from this simulation. Okay, so you can see here, this is the simulation model of space vector modulation. So here you can see the green color block. Here is actually is the modulator, the modulator of SVM, space vector modulator. So the input of the modulator is the component of vector, VD and VQ. Remember, the space vector is V. So where your V you can write into various form. One of the form is into a rectangular form, where you can set the input as VD and VQ. VD and VQ, the real component of vector and imaginary component of vector. So actually these two blocks is the sampler. So remember your modulator, all the calculation need to be updated for every sampling period. So this case it will be updated for every 1 millisecond, right? Because your frequency of carrier is 1000, then the sampling which should be inversion of the frequency, which is 1 millisecond. 1 millisecond, it will be update the calculation. And the modulator will produce, so actually we can combine these two blocks. For this case, the modulator produce the duty cycle information for duty cycle for switching status SA, SB and SC. Or we can combine these two blocks where the modulator actually produce the switching state SA, SB, SC. So mean the switching status here, it will drive the top switch for each leg of the inverter, leg 1, leg 2, leg 3. Top switch. For the bottom, you need to put the NOT gate because the switching operation is complementary. And when the top on, bottom must off. Otherwise, when the bottom on, the top must off. So that's why we need to put the NOT gate here. So here we connect the output to the RL load. So we can represent can represent the load as we can for example we connect to the 3-phase motor. So then the motor can be represented as a combination between resistive and inductive load. So we measure the phase voltage for each winding of voltage using the voltage measurement. This is the voltage measurement, VAN, VBN and VCN. Then goes to here, using the scope here. So this scope where? Scope number 2. We can plot phase voltages, VAN, VBN and VCN. So this scope can plot the switching stated waveform, SA, SB, AC. So actually we can plot the DQ voltage to verify that we have discussed maybe at the beginning of section of this chapter, mapping of voltage vectors. So you can map all the vectors available for the 3-phase inverter into DQ plane. So you have 6 active and 0 vectors. So we apply this equation. So actually these two equation is the transformation equation from 3-phase phase voltage, VAN, VN and VCN, then transform into VD and VQ. So we have derived these two equations. We just apply it. Just apply them, these equations, to plot the waveform using this scope or SY graph. Okay, SY graph and scope is different. For the scope, it will plot, for example, voltage or current versus time. The x-axis is time. For the XY graph, you can set the d-axis. For example, this case is VD. The imaginary axis or y-axis is VQ. So we plot XY mod lah, using the SY graph. Apa lagi? Okay, now we can simulate. Berapa ni? 12.5 lagi. Okay, so let's say this case before we verify. Okay, sorry. Okay, we have based on the question. You have question tadi kan? Maybe I can, sorry before we run the simulation. We try to calculate. So remember the modulator. So here is your modulator. Space vector modulator. Tak cantik lah. Space vector modulator. So this block, the input. So remember all calculation or the input will be sample for every t, which is 1 millisecond. And the input, it can be the reference of the space vector, single variable, or you can write also like this one. You can model the input as VD and VQ. This is the reference. I put the superscript star. So where the sample here is synchronized for every t, 1 millisecond. So this the modulator block is responsible to produce the switching state. Okay, SA, SB, SE. So same goes for your SA, SB, SE. So based on the information given here, your V is 30 volt and the angle is 25 degrees. So let's say from my simulation, the input I set where the modulator require the component vector VD and VQ. It's not V, just only V. So mean you have to calculate the VD VQ first. So mean from here we can write the space vector as VD plus J VQ. Berapa nak calculate? So what is the value of VD? So you apply the trigonal function, right? So where your VD, so this is your VD, right? And VQ. So your VD you apply is what? VD is cos, so the angle is 25 degrees. Cos 25 degrees, you multiply by 30 volt. And the amplitude, hypotenuse of the triangular is 30 volt. Then you get 27.189 volt. BQ, so you apply sine function. So this angle is 25 degrees. Then you multiply by hypotenuse is 30 volt. Then you get 12.679 volt. Yeah. Okay, so we apply the second approach So this is the first approach where the modulator input requires only a single variable, which is the space vector. But my simulation model, the modulator requires in terms of component vector, VD and VQ. So that's why you have to calculate these two component values. Okay. Okay, remember 27.1, 12.6. Then we can substitute. Which one? Here. Okay, ini bye. Same 12.189 for VD, 12.679. So we just put constant value based on the exercise, exercise number 2. Okay, now I can simulate the waveform to see the switching pattern waveform and also the what? Try simulate jap. Saya pun tak ingat. Okay, I simulate the file. Sorry. Banyak sangat lah tadi. Oh, sorry. Ni. So, okay. So please observe. You try to observe how the XY graph plot or map the vectors. So please apa benda please take note the sequence of the vector. Which vector have to be chosen. Maksudnya it will start. Remember, it will be started from origin. Okay. Observe properly carefully. So I continue run the simulation. Sorry. Aduh. Okay. See? Nampak? They start from origin kan? Then jump to V1. Then goes to V2. Then suddenly origin. Then actually it will be written. Okay? So maybe I can play again. Maybe I put, I need to resize this window first. Here. Okay, I try to, you observe properly. You can notice that the modulator, it will, the vector chosen start from origin, then jump to V1, goes to V2. Nampak I run back. Okay, 1, 2, 3. Origin V1, V2, nampak? Clear? Alright. So actually it will be returned back to origin. Okay, now we see the switching pattern by clicking this scope. So now you can see the top, the graph is the SA status, and middle is SB and SC. So mean for at the beginning of the sampling period 0, 0, 0, nampak refer to my mouse cursor here. Betul nampak kan? 0, 0, 0 start origin, then jump to 1, 0, 0 V1, then goes to 1, 1, 0 V2, then at the middle 1, 1, 1 origin, then turn back kan, V7, V2. V2 is 1, 1, 0 here, 1, 1, 0, then 1, 0, 0 V1, then finally go to the origin for selecting V0. Okay, clear? Okay, let's say we try to change the location of the space vector. So let's say your space vector now, instead it will be located in sector number 1 now. So let's say it be located in sector 2. So this is V1, right? V2, V3. So now we consider your vector is located in sector number 2. Sector number 2. This is sector number 1. So we can we analyze the sequence of vector. Which adjacent vector need to be chosen? Either either V3 or V2. Ni. So for this case, maybe we set your vector here. Your vector here V. We apply same amplitude 30 volt, but the angle is what? Because we need to analyze for the case the space vector located in sector number 2. So maybe we can set your space vector in line with Q axis. Q axis, so mean the angle difference is what? 90 degrees lah. Right angle kan? 90 degrees. So mean here your VD is what? So we know that your space vector is summation VD and JVQ, right? Your VD will be 0 because there is no D component vector. Because your vector is in line with the Q axis. VD is 0, right? And your VQ will be 30 volt. Is it true? 30 volt kan? Okay, then before that, tak apalah. Okay, mana simulation? This is exercise number 2, right? Okay, so your VD you set 0. 0 lah. VQ 30. Okay, then we try to simulate. Simulate. Mana ni? This one. Okay. Please observe the sequence of vector. Starting from origin, go to ni kan? So V3 V3 go first. Then select V2. Maybe I need to resimulate. Please observe carefully. Dia boleh start lagi. 0. V3 dulu. V3 first, then V2. Okay. So actually it will return to the V2, V3 and V7. V0, sorry. So now we can see the switching state waveform here. Okay tak? Betul? Starting 0, 0, 0 here, then 0, 1, 0. 0, 1, 0 is V3. Then 1, 1, 0, V2. 1, 1, 1 is V7. Then it will be repeat ni lah. Return back to the origin. Okay, clear Right. So means we have proof based on the reference signal here. Then the output here, it will drive the switching state. It will drive the power switches of the inverter. Then we try to measure the phase voltage here, VAN, VN, CN. Then we transform the three-phase voltage using these two equations. Then it will map all the vectors involved to produce the reference, the space vector reference based on the VD/VQ that we have set just now. Okay, clear? Nampak? Macam mana the way you need to you need to model kan? We are using the simulation MATLAB to set the sequence of the vector. Of course, you need to set properly dia punya timing information. The time taken for the vector to be switched. TA, TB, TZ. So this is the black box. You need to understand lah. Test your understanding. Try to model these two blocks. This is the idea lah. Maybe the assignment I can provide or we can discuss in detail after Raya. After semester break. Okay. Berapa dah? Now is 12:40. Lambat lagi raya kan? Okay, I want to demonstrate another simulation file. This is the complete version. Yeah, so maybe this one I need to minimize first. Okay, so this case, the input of the reference, nampak before this, in the previous simulation model, I put a constant block because we just need to verify that what we have done for the exercise, where we just analyze at a particular instant of the space vector. Maksudnya your punya V is 30 volt and the angle fixed at 25 degrees. So that's why I just put the constant block here. Nampak yang tadi simulation tadi. This simulation. Ni, simulation. This one for the case when the sector in sector 2 lah. Okay, but in practice, actually the input or the reference of the space vector or we can put the VD and VQ actually is the sine waveform. So mean your space vector practically it will be rotated to form a circular locus. Trajectory of circular. Maksud dia akan rotate to form a circular which is centered at origin. So this case to prove the calculation that we have discussed in exercise 2. So let's say we set your amplitude is 30 volt. Remember your punya exercise tadi your punya amplitude is 30 volt. This is for VD. The modulating the fundamental frequency is 50 Hz. So you must now to differentiate between the fundamental frequency and the carrier frequency. Carrier frequency will determine the switching frequency of the inverter. But the fundamental frequency, that one for your output of the inverter. Your linear frequency 50 Hz. This one is VD 30 volt. VQ amplitude is same 30 volt. Frequency also same, but you must have phase different. Remember your D and Q, the different phase must be 90 degrees. For ABC, VA, VB, VC, the difference between two phases is 120. But for the direct and quadrature waveform, VD and VQ, the different phase you must set 90 degrees. 90 degrees. Okay, ni 90 degrees Okay, your amplitude 30 volt. So then we can verify. Macam mana nak buat tadi? So this is the complete model. So let's say we try to plot the switching state here. Okay, maybe I can run the simulation. Run the simulation, then we can observe this one. Where scope mana? Ni. Nampak? So you please analyze the way the modulator switch the vectors. Nampak? So let me pause first. Let me continue then pause. Okay. So this case you refer from the XY graph number 1. So remember because your system is balanced system. Your amplitude of the VD VQ are same. The angle difference 90 degrees. So mean it will produce the balance system kan. So where your space vector must be rotated in circular, circular shape. So this case, it will be rotated in counterclockwise, and depends on which one will be lead, either VD or VQ. So this case, when I pause, your reference voltage vector is located in what sector? Sector number 2, right? Sector number 2. So then the modulator will map the vector V2 and V3 and V0, right? Ni. So let's say I proceed, continue the simulation. So then you can observe when your space vector is now within sector 3. So then you can expect that the vector selected should be V3 and V4. Okay, I continue to run the simulation. Okay, now sector 3. What? Sector 3. So this is the way how the modulator switch the vector. Okay, then you can refer from the switching state here. So means starting from 0, 0, 0 at origin, then 0, 0, 1, 0. 0, 1, 0 means vector, which vector? V3, right? V3. V3 come first. The first adjacent vector to be chosen is V3. Then you will choose V4. V4 is 0, sorry. Which one? Maybe 0, 0, 1, 1. 0, 1, 1, I think. 0, 1, 1. Then 1, 1, 1 at the middle. Then it will be return. Okay. Okay. So to make the simulation faster, so you need to close the SY graph. Plotting. Because due to the computational burden to plot the XY mode, so you can close the SY graph, then your simulation running faster. So then you can see the result of the phase voltage by clicking this scope. Ni VN, BNCN, you measure using the voltage measurement each phase you connect with the voltage measurement. Then this waveform, this is the phase voltage. Nampak? Okay, so you have the switching pattern for the VAN, VBN, VCN. Same pattern, but each phase has different phase by 120 degrees. And mean VAN come first, then followed by VBN by 120 degrees, then VC followed by VN by 240 degrees. Okay. Okay, then we can see the amplitude because the reference we put here is 30 volt. Okay, so the reference you can verify the amplitude by observing the frequency spectrum component of the output voltage. So here you can double click the power GUI block. Go the tools tab here, FFT analysis button, click OK. Then from here, actually they move to my first monitor here. Okay, so this is the waveform. Using the FFT analysis tool, then you can click the display button. So mean we expect the amplitude voltage must be 30 volt. 30 volt. Click the still, then you get here. The fundamental here is 30. Almost same lah. With the calculation. The calculation is 30 volt. But simulation result, the answer is the result is 29.9. Almost similar lah to the calculation value. Okay. So you can see the fundamental component here, which is located at 50 Hz. Boleh nampak 50 Hz here. So mean the length or the amplitude is almost 30 volt. Okay. So this is the nearest harmonic, where the location of the nearest harmonic is located around 1 kilohertz. Because we set the triangular frequency or the carrier frequency at 1 kilo. 1 kilohertz. This one. So mean the nearest harmonics are located around 1 kilo. So in order to minimize the filter size, so you need to push the location of the nearest harmonic at higher frequency, maybe 10K, by adjusting the triangular frequency. So mean you need to change the triangular frequency from 1 kilo to 10 kilohertz. So then you can minimize the filter size. Okay. Clear? So maybe I can plot here. So let's say I try to plot the mapping of vectors here, VD, VQ. So this is the figure 1. Dia punya mapping of vectors. Then the reference. Okay, so maybe you can refer from the simulation model. This is the simulation model where the reference to sine wave here, I plot using the scope ni, workspace ni. To workspace VD. So I put the variable as VD1 for VD and VQ1. VD, VQ tadi as the output here. You map the mapping of vector based on the phase, the output of the load ni, and the output voltage. You measure using the voltage measurement, then you transform to produce the VDVQ. So VDVQ actually plot the mapping of vectors here, the hexagonal ni. So then for the reference, I use VD1 and VQ1. I use VD1 and VQ1, the reference. So in order to plot in a same graph, so you need to write something like here. You must type whole first. Then you write VD1 and VQ1. So maybe here, in order to differentiate between these two waveform, for the output, sorry, the reference VD1, VQ1, I draw the graph with red line color. Sorry, red line. Okay, so I enter. So then you can see the result here. Nampak? So because the length of the vector, the active vector is 2/3 VDC, but you set the reference is 30 volt. So that's the radial component of the circular locus is 30 volt. Ni. Right, 30 volt. X is 30. Y almost 0. 10 minus 15 dia punya power kan. Okay. So this is the output. Okay, now let's say we try to simulate. Ni kejap lagi. Let's say we try to simulate what is the maximum possible voltage can be produced using the SVM. So mean the amplitude of the reference, you must set what value? Remember? So this case, if you look at the page here, nampak? And by using SPWM, the maximum possible voltage is half of VDC. So mean let's say you set VDC tadi 100 volt, so the maximum is 50. And you cannot fully utilize the DC voltage of the inverter. But SVM, actually you can expand the circular and dia akan grow until the circular shrink or grow touch to the hexagonal line here. Ni. For example ni, the red line, the dash line circle here. So this is the maximum voltage can be produced using SVM through the linear modulation region. So where the radial maximum is VDC divided by SET3. And you can obtain this value because, for example, V2. To plot V2 is summation between VD and VQ. So where your V2 is VDC divided by SET3. So actually you can obtain from here. V2, where V2? V2 is here, this one. And so the VQ maximum is VDC divided by SET3. So mean this is the maximum radial component of circular locus. So means here VDC divided by SET3, you can change this value as VDC is 100 volt. This case VDC is 100 volt divided by square root 3. Okay. So we put the maximum possible voltage here. Control C, copy. Then same goes to VQ. We apply the same amplitude value. So the VDC, I forgot to show you in this one. We said the DC voltage is 100 volt based on the example. Exercise. 100 volt. Okay, now we try to simulate to see the maximum possible output voltage can be produced from the what? From the SVM using the SVM technique. Okay, so this is the locus. So in order to make it the simulation running faster, you need to close this plotting because due to the computational burden to calculate because there are graphic involved kan. So then you can see the simulation faster So then to verify the fundamental, the maximum voltage, you click the power grid block, go the tool tabs, FFT analysis. Then here, you click the display button. Now the value, the maximum fundamental is 57.5. You set the amplitude value what? Mana? This value kan ni. Okay ni. Sorry ni. 100 divided by square root of 3. So mean the value will be what? 100 divided by square root of 3. 57.7. Almost same lah. So this one is 57.5. But the calculated or theoretical value is 57.7. So the error may be less than 5%. So the result is acceptable. Okay. So you can see the length or the amplitude of the fundamental component, which is located at 50 Hz, reach at 57 here. 57 here. Okay. All right. So okay, locus. How about the locus? So this is for the previous kan, where the amplitude is 30 volt. But for the maximum case, maybe this one I plot using figure number 2. Figure 2 figure 2. Okay, then we plot VD VQ first for the mapping the vectors and 6 active 2 zeros. So make sure you type whole because we need to put two result in the same graph. Then you type VD1 VK1. So this one in red color. Okay, then we try to compare. Ni. Okay. There. So now you can see the circular grow up until it touch to the hexagonal line. Okay. So this is the maximum possible voltage can be produced using space vector. But if you apply sinusoidal pulse width modulation, it cannot be touch to the hexagon. Because the amplitude, the maximum amplitude is half of VDC, 50 volt. Okay. Habis. Okay, so we complete for chapter 2, space vector modulation. So the way how to set the sequence of vectors, how to model the simulation for calculate the timing information, that one is for your assignment. I cannot expose lah the detailed discussion kan ataupun calculation or equation how to model the modulator, the SVM modulator. That one you need to you can explore lah by your own for test your understanding to verify what that you have discussed or that we have discussed in class. Then you can try to verify through the simulation. Okay. So maybe we can discuss in detail how to model the SVM in your for tutorial session. Okay. Maybe you can come to the lab, then you form groups. So maybe one group maybe have 5 numbers of students. Each group must bring a laptop or computer. Then we can discuss in detail how to model and in detail the space vector modulator. Alright. Senyap ini. Any question? Dah pukul 1 dah.
Doktor,
Yes.
boleh buka slide yang sequence of switching vector sector 6 tu.
For the case what? Sector 3.
Sector
Which sector?
6.
Sector 6. Here is sector 6.
Dia punya untuk interval 2 tu dia kena pilih choose V1 lah kan, bukan V5 kan?
V1. Oh sorry. Yeah, V1, sorry. So for interval number 2, you must choose V1. The modulator choose vector V1. V1 kan? V1 because switching only occurs in phase A. Right. V1. Sorry V1. Then switch to V6, V7, here V6, then here must be V1. Okay, thanks for the correction.
Baik, tu saya tahu.
Okay, any question? Oh, dah berasak kepala If no question, maybe we can end our lecture now. So, ada nak tanya lagi? Tak ada? Yang sini tak ada? If okay, doesn't have question, then we can end our lecture. Then see you after semester break. For midterm, how about the midterm? Midterm, no need to ni lah. So maybe we can conduct for midterm test maybe around week 10. Objective question for space vector modulation. Only objective question, SVM. Simple. Okay. So thank you for attending my class. And selamat Hari Raya. Happy holiday. Nyap.
Thank you Doktor. Selamat Hari Raya.
Hari Raya. Jaga baik.
Thank you, Doktor.
Don't drink and drive. Jangan main mercun.
Yang main mercun.
Boleh main mercun. Kena pandai-pandai lah. Okay.
Kena ajar doktor main mercun.
Stop recording.